Hello everybody, my name is Alejandro Pardo and I am here on behalf of my team to present Budget-Aware Object Detection, BAOD. My man Shu and I contributed equally to the development of this paper. This work was done while I was a student at BCB Andes and a research intern at IVL at KAUST. In this work we're going to study object detection, which consists on finding objects of interest in images. Usually the location is specified with a point, a bounding box, or the center of the object. There are a lot of applications doing this, like automatic face detection, pedestrian detection, video surveillance, among others. Training state-of-the-art models requires large amounts of data. And depending on the level of supervision, there is the need of different kind of levels for every image that you collect, which results in a very, very expensive process. One of the most important benchmarks in object detection is Pascal BOC. Pascal BOC required around 700 person-hours to annotate around 10,000 images, and more or less is calculated that 34.5 seconds is required to draw a bounding box and 1.6 to decide whether the object is in the image or not. In average, 252 seconds were required per image, including error corrections. To build an object detector, we assume that we have a budget. This budget has to be split up between the next things. First, the image collection, then the annotations for these images, and of course the computation cost to train models on this data. So the first dimension is the image dataset, in which we're going to scrap the web or get the images from somewhere to collect a large amount of data. After this, there is the annotation scheme, in which we are going to collect these images and we are going to either annotate with strong labels, which is instance level labels, in which we are going to draw the bounding box or whatever indicates the presence of each instance in the image, or weak labels, in which we are going to just decide whether the object is present or not in the image. Finally, the detection model can be either fully supervised, in which you have access to the bounding boxes at training time, or weakly supervised, in which you don't have access to the bounding boxes at training time, but you still produce bounding boxes at the end. Now, what is the problem of this standard approach? If we fix the model and the training scheme, and we train on different percentage of the data, we find that with the 50% of the training data, we can achieve the 95% of the total MIP, meaning there is data redundancy and we are not spending the budget on data smartly. To solve this, we want to build budget efficient detectors. We want to explore the first two dimensions of the problem, being data and the annotation scheme, and we want to propose a new evaluation framework. For the first dimension, we're going to use active learning to explore which images to choose and to annotate. For the second dimension, we have one of two options. Fully supervised object detection, which use only strong annotations. Weakly supervised object detection, we use only weak annotations. Usually, weakly supervised object detection is way behind fully supervised, since from the MIP perspective. However, this comparison is not fair, because weakly is cheaper than fully supervised, and in weakly supervised we only use weak labels. To make this comparison fair, we need to take into account the training budget. When the budget is large enough, one can annotate many images as one wants with strong labels, and then fully supervised is the way to go. When the budget is small enough, one can have more images with weak labels, and then maybe weakly supervised is the better option. We combine weakly and fully supervised annotation strategies within an active learning framework that is able to do hybrid learning using the two annotations. Our solution allows to annotate with weak and full labels and train with all of them at the same time. At every step, the agent is going to decide whether to annotate images with weak labels or with strong labels from a big pool of images. To pick the images that we are going to annotate at each step, we're going to study three sampling functions: random, percentage score, and learning active learning, or LAL. For our final solution, we're going to decide what to do with each image based on an optimization policy. We're going to pick among three actions, being X1, labeling strongly from unlabeled data, X2 labeling weakly from unlabeled, or X3 labeling strongly from weakly labeled already. We base our optimization in two scores, being uncertainty score, in which we want to maximize this objective function, or LAL score, in which we want to maximize this objective function. Our experimental setup consists on Pascal VOC, in which we're going to use either Pascal VOC 2007 with 5,000 trained images or 2012 with 11,000 images. Every time we're going to be testing on Pascal 2007, which contains 4,900 images. For the image annotation cost, we're going to assume that a strongly annotated image costs 34 seconds and a weakly annotated image costs 1.6 seconds. We're going to assume that each image contains 1.37 object instances, which is the average for Pascal, and the maximum budget that we're going to take into consideration to solve the optimization is going to be the cost of strongly annotated Pascal VOC train val set, which means the cost of strongly annotating 1.37 boxes for each of the 5,000 images. For the evaluation metrics, we created our own metric. We first construct the budget performance curve. It consists on what is the mean IP based on the percentage of the budget that we have spent already. We divide this curve in three regions, which is low budget, mid budget, and high budget. The region between 80 and 100 is negligible, since the mean IP doesn't change that much, so we ignore it. For the implementation details, we use FastRCNN as our detection model, and we use VGG as the backbone for FastRCNN. Under this setup, we're going to present now the experiments. The first experiment, we're going to show what are the baselines for the sampling methods given the fully supervised object detection pipeline. Then, we're going to show what are the advantages of including hybrid training, to finally show what are the advantages of combining hybrid training with our optimization-based solution. So, for the baselines of the sampling method, we have this random sampling, maximum uncertainty sampling, minimum uncertainty sampling, and LAL. So here we see that uncertainty sampling maximum is the best behaving method. Now, when we include hybrid training, we see that we can improve the random sampling, and we can also improve the uncertainty sampling. To study our optimization-based method, we set up two of the base methods from before. Now, we study what happens when we use LAL as our base optimization, and we see that we already improve under almost all the ranges of budget. However, when we include our optimization based on US or uncertainty sampling, which is what we call BAOD, we see that we improve on all the ranges of budget. Here, we present a very simple qualitative result in which we see that across the steps, our method prefers to annotate hard images with multiple objects and hidden objects with strong supervision or bounding boxes, and prefers to annotate with weakly annotations images that have center objects, which is an interesting finding. We propose an additional experiment to show the effectiveness of our method. We're going to give to our method an infinite pool of images, which is going to be the combination of Pascal 2007 and 2012. And we are going to give the model the same budget to spend as it was spent in Pascal 2007. When doing that, we found that we can reach the same performance 0.71 of the original model by spending only 87% of the budget. More importantly, when we spend 100% of the budget, we can achieve a 0.73 mean IP, which is 2 points more in MIP that we are gaining just by picking better the images that we train with. To conclude, we propose to study object detection from the annotation budget perspective. By doing this, we achieve the same base model performance while saving 13% of the annotation budget. And even better, when using 100% of the budget, we improve the performance by 2% just by picking how and what to annotate. Thank you everyone. This was BAOD, Budget Aware Object Detection.